Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 38. Here we are going to start a new physical chemistry chapter from the curriculum, the solid state. First of all, let us have a look on the subtopics in this chapter, and these are unit cells, Miller indices, crystal systems, and Bravais lattices, elementary applications of vectors to crystal systems, X-ray diffraction, Bragg's law, structure of sodium chloride, cesium chloride, potassium chloride, diamond and graphite, close packing in metals and metallic compounds, semiconductors, insulators, defects in crystals, lattice energy, isomorphism, and finally heat capacity of solids. All these subtopics are divided into 14 number of lectures, and lecture number 2 is subdivided into 4 parts. Lecture number 3 is also subdivided. It is subdivided into 2 parts. So overall, you are going to have 18 number of videos on this topic. So let's begin with lecture number 1, where the subtopics are unit cells, Miller indices, crystal systems, and Bravais lattices. So let's start with the definition of unit cell. Before that, let's say a few words about that. When a solid substance is considered, it is basically rigid in nature. It may be crystalline or it may be amorphous in nature. So when a solid crystal is broken into small pieces, then the smallest piece that geometrically resembles the shape of the entire crystal, it is known as the unit cell. This smallest building unit is made up of symmetrically aligned group of atoms. Simply, unit cell is the smallest building unit of a crystal structure, just similar to a brick, which is the smallest building unit of a wall or monument. So what is the definition of unit cell? The definition is, a unit cell is the smallest group of symmetrically aligned atoms which can be repeated in an array to make up the entire crystal. Next subtopic is Miller indices. The term indices is the plural form of the term index. This is the way how a lattice plane is described by a combination of 3 numbers. According to the terminology of crystallography, the x-axis is called the a-axis, y-axis is called the b-axis, and the z-axis is called the c-axis. Now, this is an imaginary plane which cuts or intersects the a-axis at this point. The point of intersection on b-axis is this one, and the point of intersection on c-axis is this one. Now, the distance of the point of intersection from the origin along a-axis is h prime, that along b-axis is k prime, and that along c-axis is l prime. Now, this is the unit cell which is aligned along these 3 axes, and the edge length along a-axis is small letter a, the edge length along b-axis is small letter b, and the edge length along c-axis or z-axis is small letter c. The ratio of a and h prime is called h. The ratio of b and k prime is l, and similarly the ratio of c and l prime is l. And when h, k, and l, after clearing the fractions, are obtained as integral numbers or whole numbers, then this combination of 3 numbers is called the Miller indices of that imaginary plane. Now, crystal systems. So, inspection of wide variety of crystals leads to the conclusion that all can be built up only from 7 basic regular figures or subunits, and these are known as the 7 crystal systems. What is the definition? The definition is, a unit cell is in the 3-dimensional lattice is characterized by the unit cell parameters. So what are the unit cell parameters? Now, the unit cell parameters are the edge lengths and the corresponding angles between 2 intersecting planes. From these parameters, a total of 7 parallelepiped shaped crystal lattices can be constructed, which are known as the 7 crystal systems. So these are the pictures of the 7 crystal systems. This is a cube. Cube is the noun form, cubic is the adjective form. This is a tetragon. This is an orthorhomboid. What about the descriptions? All the edge lengths are equal, so a equals to b equals to c, and the corresponding angles between the 2 intersecting planes are also equal, and they are 90 degree for a cube. You can Find resemblance or similarity of this tetragon with a toothpaste box, where A equals to B not equals to C, while alpha, beta, gamma are all equal to 90 degree. And you can find similarity of this shape with a matchbox or simply a book, where none of the edges are equal with each other, but the angles are equal at 90 degree. So this is this is an orthorhomboid, and the four remaining are rhombohedral, hexagonal, monoclinic, and triclinic. So rhombohedral has another name, trigonal. Okay, and the structure is, it is a structure of trigon or rhombohedron. This is the structure of a hexagon. This is the structure of a monoclinicoid, and this is the structure of triclinicoid. So what about the characters of rhombohedron? This is A equals to B equals to C, alpha, beta, gamma, or all are equal but not 90 degree. That means all the 6 faces are rhombus. For a hexagon, the 2 edges are equal but the third one is unequal, while 2 angles are 90 degree and the third angle is 120 degree. While in case of monoclinic structure, none of the edges are equal, 2 angles are 90 degree but the third angle is not equal to 90 degree, while in case of a triclinic structure nothing is equal. Now Bravais lattice set, but before Bravais lattice we should have idea about space lattices. There are 4 different types of unit cells known as the space lattices, and these space lattices are actually formed from the basis of lattice point distributions. How? Like this. Here we have 4 unit cells, but the lattice point distributions are different. This is all the 8 corners or 8 vertices are occupied, while in this case, along with 8 corners, the 6 faces are also occupied by a central lattice point. While this one, along with the 8 vertices, there is a body central lattice point also. And here, only 2 faces are occupied by a lattice point. Now, why this face is called C face? Because this face is perpendicular to the C axis, or this is the base. So that is why it is base centered or C face centered. So these are the 4 space lattices. Now this is made up of 8 lattice points. This is 14, this is 9, and this is 10 lattice points. But 1 out of 8 is inside the primitive lattice, space lattice. Here 4 are inside the face centered cubic space lattice. Here 2 are inside the body centered cubic space lattice, and here 2 are inside the body centered cubic space lattice. So primitive has the symbol P, face centered has the symbol F, body centered has the symbol I, and face centered, base centered has the symbol C. And what about the volume occupation? The volume fraction, that means when they are closely packed, then maximum volume is occupied. So what should be the maximum probability of occupation of volume? So the volume fraction is this is the lightest one, that is density is lowest here, and here the density is highest because this is the most closely packed space lattice. Here it is 0.74 and here it is least 0.532, and this is the intermediate one, 0.68. So the volume occupation according to percentage, this is 52.3%, 74%, and this one is 68%, and the 100 minus these values are the void spaces. Now move on to the main topic, the Bravais lattices. Look at the pronunciation. It is written, the spelling looks like Bravais, but you have to pronounce it as Bravais. Okay. Now, unit cells have 2 types of symmetries, internal and external. External symmetries are what? The center of symmetry, the plane of symmetry, the proper axis of symmetry, and the improper axis of symmetry. While the internal symmetries are the screw axis and the glide planes. From rotation, you can get the screw axis, and from translation, you can get the glide planes. These are internal symmetries, and according to the internal symmetry, you can get the Bravais lattice. Okay, but we have 4 space lattices and 7 crystal systems. If you combine them, then there are 28 number of possibilities which can be obtained. But according to the internal symmetries, 14 out of 28 are available in nature, and remaining 14 are not available in nature. So what about the definition of a Bravais lattice? Look, crystal lattices can be classified by their translational and rotational symmetry. In three-dimensional crystals, these symmetry operations yield 14 distinct lattice types, which are called Bravais lattices. Here, look, translational symmetry is giving the glide planes, and rotational symmetry can give the screw axis. Now, the 14 Bravais lattices. A cube may have 4 space lattices, but one is not possible naturally, and this is the base-centered cubic structure, which is not possible. Tetragon has 2 possible and 2 not possible, simple and body-centered, but face-centered tetragonal and space-centered tetragonal are not possible. Orthorhombic is the only crystal system that has all the 4 space lattices: the simple orthorhombic, base-centered orthorhombic, body-centered orthorhombic, and face-centered orthorhombic. The remaining 4, monoclinic has 2, and triclinic, trigonal, and hexagonal, all these 3 has only one, simple. Monoclinic has simple and base-centered. And these are the structures: simple cubic. This is the structure of simple cube, body-centered cube, face-centered cube, simple tetragon, body-centered tetragon. This is a simple orthorhomboid. This is a body-centered orthorhomboid. This is a base-centered orthorhomboid, and this is a face-centered orthorhomboid. Now, simple rhombohedral can also be called simply rhombohedral because it is the only one, no other possibilities. Similarly, hexagon, in case of hexagon and triclinic, they are also called only hexagon, not simple hexagon or single triclinic. Okay, and monoclinic has 2 structures. One is simple monoclinic, and the another one is base-centered monoclinic. So that's all about the first lecture. Now let's solve some questions. So this question came in IIT-JAM 2024. The question is the unit cell of a 2-dimensional square lattice. So this is a 2D lattice, square lattice. Okay, so with lattice parameters A, which is indicated by the dashed lines. So from here to here it is A, here to here it is A, and this is R, that is the radius. Okay, so the percentage of occupied area gray, that is radius R, and the gray area, that is this shaded area, 1/4 of this circle, 1/4 of this circle, 1/4 of this one, and this one. That means 4 into 1/4. Is it? So the edge length A is twice R, hence R equals to A by 2. Now we have 4 quarter of circles, so 4 into 1/4 into surface area of each circle, which is pi r squared. Now R is A by 2, so this pi into A by 2 whole squared, and this is 0.79 A squared. Now when 0.79 A squared is divided by the surface area of the whole square, which is A squared, then A squared cancelled, only 0.79 is left, and the percentage is 79%. So the correct answer is 79. Now the question number 2, the volume fraction in an element in an FCC lattice is, we know that the volume fraction of primitive is 0.523, FCC 0.74, and BCC 0.68. So the correct answer is 0.74. Here is the top view of the face-centered cubic lattice. You can see here 5 spheres out of 14. This is one of the surfaces, and here it is the top surface, and this is the diagonal. Now this is the lattice point, and each sphere is equivalent to a C60 molecule. You know that C60, that is Fullerene molecule, looks like a football, and this is the center of gravity of the football. So we have to find out the distance between this point to this point. That means the minimum distance between 2 centers of Fullerene molecules. So we know that this distance, okay, first of all we have to say that each C60 molecule is equivalent to a sphere in the top view of this face-centered cube lattice. Now the smallest distance between the centers of 2 C60 molecules is twice R. This is the distance. Here to here is 1 R, and here to here the twice R. Okay, so here to here twice R is the distance. Now here to here 4 R is the face diagonal of this unit cell. And what is the face diagonal? It is A root 2. So this way we have to calculate. So face diagonal A root 2 is equal to 4R. So what is the value of 2R? 2R is A root 2 by 2 equals to A by root 2 equals to, the value of A is given as 14.14 angstrom. So 14.14 angstrom by root 2 angstrom. We know root 2 is 1.414. So it is 10 angstrom. So the correct answer is 10. So that's all for this first lecture. Thank you and have a nice day.